So today's flip lesson is the first part of chapter 10. Um, chapter 10 is on geologic time, but the first sections are about fossils and how do we know what happened in the past. So yesterday you read about what is a fossil, what types of fossils, and how do they form, what do they tell us. So let's take a look here. So a fossil, who could tell me the definition of what is a fossil? So a fossil is preserved remains or evidence of living things. And so most commonly when we think of fossils, we think of fossilized bones, fossilized skeletons, that sort of thing. We can also have fossilized footprints or eggs or nests, evidence that something used to live there. You can also have, one of my favorites, you can also have fossilized poop. Fossilized poop is actually known as coprolites. Coprolites. The reason why it's called, no, the best thing is that the reason why it's called coprolites is that as scientists were studying these things, there were these two scientists who were very, very competitive. And the one was named Cope, and the other one, ironically, I don't actually remember his name. I always forget. I think it was Marsh. But anyways, these two guys were in direct competition. And when the other guy discovered the fossilized poo, he was so irritated at Cope that he named a fossilized poo um, after his rival. And ironically, that way I remember his name. But anyways, so what can fossils tell us? What kind of things could we learn from fossils that we might find in rock? So the different fossils are going to tell you about the environment. An index fossil is a fossil that is very common for a specific amount of time. And then it's gone. So the index fossil being common for a very specific amount of time and then not there after that is going to tell you something, because trilobites, for instance, which are those, they kind of look like roly-polies, and they were aquatic, they lived in the water. And they were very, very common before the dinosaurs in certain ages, and then they weren't there anymore. So if you find the trilobites, you know that it was in that particular era. If it was before, and so the fossils before or after would be there. Dinosaurs are not exactly an index fossil, but it's a similar idea. We know that the dinosaurs went extinct 65 million years ago. So if you find fossils of things with dinosaur fossils, you know that that thing is older than 65 million years old. You know that because of the presence of these particular fossils. So that's what an index fossil is. It helps you put things in order. Okay, and these, of course, are all images from the book just about how the fossils form. Fossils form in sedimentary rock most often. In this example, the animal dies and sinks to the shallow water, gets covered up, and over time becomes rock, preserving the animal, and breaks up. In most cases, it's actually fairly rare to have a whole entire living thing. Fish fossils, because they live in the water and might end up buried, are more likely. But normally when they find fossils, they just find bits and pieces. Teeth in animals, same as in humans, are a very hard substance, and so teeth tend to be something that fossilizes more readily than other bones or soft tissue. There's actually one place just north of Boulder where there's this stone called Niobrara, and you can find fossilized clamshells in it, and I've gone and done that. It's just on public land. Also here in Colorado, in Florissant, there's fossilized trees, and there's fossil beds there. So we definitely have that in Colorado. All right, let's see what's next. The law of superposition. This is going to be like a couple weeks ago when we learned, what was that other big annoying word? No. Uniformitarianism, right? Uniformitarianism. Uniformitarianism is obvious but useful. Uniformitarianism was that the processes that happened in the past, or that happen now, happened in the past. And living things act in the past the way they act now, right? So if pine trees need a particular environment, right? So because without that you can't really make assumptions about the past. So the law of superposition, does anybody have this from what you read yesterday? It is the super obvious observation that um, in undisturbed sedimentary rock, so pretty obvious because layers form and then newer layers form on top of them and new on top of those. So in undisturbed sedimentary rock, the deeper layers are older than the layers on top, and the layers on top are newer. So again, this is obvious, but we all have to agree on this. And this is not just a hypothesis or a theory. This is a law, scientific law, pretty big deal. And by saying this, then you can say, oh, like I was just mentioning with the dinosaurs, if this layer of rock with these particular plant fossils is deeper down than T-Rex, then we know that it is older in time than however many million years ago the T-Rex existed. So it allows us to do what's called relative dating, which is not an actual number, but saying this is older than this and this is older than that. Now you might be thinking undisturbed sedimentary rock, what does that mean? Well, what that means is that sedimentary rock would form in horizontal layers, of course. This is undisturbed sedimentary rock. So which layer is the oldest? And this one is the newest. Pretty obvious. And if you ordered them, so this would be 1, 2, 3, 4, 5, 6. Okay, but what can happen to sedimentary rock over time? It can get folded. It can there can be faults. It can get tilted. So what might happen is you have something like this. There's tilting or there's disruption to the layers, and then so now you've got them kind of twisted. They can also actually twist where it actually turns over. But then there's erosion, and then new layers get laid down on top of it. So here, this is an unconformity. This isn't so much the layers are out of order, but what this is that there are layers missing. So in the original one, it goes brown, black, blue, red, and then here, it's going to go brown. There is no black or blue or red. Those layers are totally missing in this area, but over here, you would still have them. So in some areas, you're going to be missing layers or have layers out of order. We know around here you could also have something happen where you've got these layers, and then at some point, they actually get tilted upwards like this, right? And that's where we see like the flat irons or some of the ridges if you're driving along the Front Range. And then, so if rock falls down or whatever, this could be the flat irons. And then you get other layers down here, then they're not necessarily going to be in order because they're no longer in the order they got laid down in. Anyways, pretty straightforward, right? Make sense? Alrighty. And another thing that can happen to the layers, and in your second worksheet, there's some pictures like this. You can have igneous intrusion. Igneous rock is magma or lava. And so here's the original rock. And you've got, so according to the law of superposition, this extrusion is older than the shale above it, of course. This is older, this is newer, because that's the order they formed in. And then here, what if there was a weakness, though? This intrusion, this magma, cut up through here. And so you know this has to be newer than this because the shale had to be there for that igneous intrusion to form, right? The igneous intrusion wouldn't just make like a random tower and the other layer form around it. Does that make sense? You're going to see a couple of different pictures like this. Here's one. But it's an activity that you're going to see, which is that when I say which layer is the oldest, then you might look up and you'll see an igneous intrusion like this. And you'll say, okay, well, obviously, this igneous intrusion labeled X is going to be older than, and then younger than. So which, this igneous intrusion, if you're looking through the layers and you saw this, which layers existed before it formed? Which layers had to be there already before this formed? A and B probably formed after it, so whatever this layer is. So AA and A were already there, and then this formed, and then B, C, and D formed after it. Does that make sense? Okay. Relative dating, not as creepy as it sounds. Relative dating is simply putting layers in order, and it doesn't actually give a number date to them. It's not telling you how old it is, just that this one is older than that one. So it's putting them in order of oldest to youngest. Which one's older than which other one? So relative dating is not going to give you a number. Relative dating is going to say layer B is older than layer C. Layer A is older than layer D. Absolute dating gives an actual number date. Actual number of how many million years ago. Now, how are we going to know how old rock is? Is there any way to know the actual number? Obviously there is, because it's called absolute dating. Anyone know how we find that actual number? No. We find it through radioactive isotopes. Ah, yes. Radioactive dating. And radioactive dating is a little bit confusing. We're actually going to watch the brain pop on radioactive dating. There's carbon-14 dating, which will tell you how old things are that are in the thousands of years old, and that there's uranium dating that is things that are older than that. So I will put on that brain pop. It is the brain pop. It's actually called carbon dating. And then that's the activity in the book. That's similar to your worksheets today. So let's go ahead and do the brain pop, and then we'll work on the next worksheets.